Today, our learning will be on the topics enthalpy, entropy, and free energy. Beforehand that, we summarize our understanding about three different laws of thermodynamics. So, first law of thermodynamics, what it is about? It talks about heat and work. Both forms of energy can transform one to another. If you take any process, energy can be changed from one form to another form, including heat and work. So it is never created or destroyed. So it also giving hints to or indicates to conservation of energy. Now, about second law of thermodynamics, what we understood that we are going to get the definition of the term entropy, the degrees of randomness. Entropy is a measure of disorder, and entropy of an isolated system, it will increases any spontaneous process. Now we also know what is isolated system. In such system, no mass can or energy can enter into the system from the surroundings or goes out from the system towards the surroundings. Or you can tell second law predicts that the entropy of an isolated system always increases as time progresses. And now we are going to understand about or discuss about the third law. The entropy of a perfect crystal approaches to zero magnitude as temperature approaches absolute zero. If anything you are talking about thermal entropy, then the word perfect crystal is not important. Absolute ordering is not required. So thermal entropy is tends to zero as the temperature approaches or tends to absolute zero. These are the three laws we have understood. Now we are going to understand the enthalpy, entropy, and free energy and how they are related and how they are going to be important with respect to any kind of transformation or reactions. It may be chemical reactions or any kind of phase transformation, anything, any change from one state to another state is going to happen. In this regard, enthalpy, entropy, and free energy are very important, and they are going to play very significant role. So first we can understand that enthalpy. What is enthalpy? Enthalpy is basically the heat content. Is required heat to raise certain temperature. So enthalpy is directly related to internal energy and work done in the form of pressure multiplication by its volume. And already we understand that dH equals to Cp dt, and if you want to calculate H, then 0 to T Cp dt we have to calculate. And the free energy gives free energy is equal to enthalpy minus temperature in absolute scale multiplied by entropy. So stability of a phase is related to free energy. So you can understand the stability of any phase is actually dependent how minimum energy state it is there, how minimum free energy state it is there. So if you are talking about change in free energy or del H, then you should tell that should be negative, so that it should be minimize the energy. Then only the transformation will take place. So thermodynamics actually talks about stability criteria as well as feasibility criteria. So when you are going for differential form of free energy, then you are talking about feasibility of that particular process. And if you are talking about the exact that G form of the free energy of a particular system, then it talks about the stability of that particular system or particular space. So we can tell that stability of a phase related to its free energy. Later on we will understand that why it is not related to enthalpy or entropy. It's why it is related to only free energy. That we can understand as we goes on with this lecture. Now, generally, we used to set up a conditions because room temperature we are going to take that enthalpy at 298 Kelvin temperature or room temperature. The usual assumption is that in the standard condition, the enthalpy is equal to 0. And if you scale that way through that assumption, then after that, whatever the things you are going to calculate above the temperature, then at that time you are going to get certain positive enthalpy, and less than that temperature you are going to get negative enthalpy. Actually, metallurgical and chemical field, most of the process, most of the reactions, most of the transformation are basically people talks about room temperature or higher temperature. Very rare people used to talk about sub-zero temperature application or sub-zero temperature process. So that's why getting such kind of standard condition is good or very practical for a metallurgical engineering branch or any chemical engineering branch. Now, if you check that Cp versus T plot, this is on kind of S-like plot, and the maximum value is around 3R approximately. It can be 3 to 3.6, 3.7, that way it varies, but around 3R. And the important part is that the absolute zero sections. Already we know that at T tends to 0, Cp also tends to 0. No vibration is there. So in this case, we can tell that at absolute 0, the Cp is 0. That is very important because it actually helps you to understand that at that condition, the entropy is also 0. How? The ds equal to Q by T. This is the entropy definition. And at constant pressure, that Q can be substituted by dH. So dH by T in the absolute scale. If you get that, since dH equals to Cp into dt, so dH equals to 0 now. So ds also 0. So at that temperature, you can tell the entropy also tends to 0. That is actually third law of thermodynamics. Now we are going to discuss about a new kind of plot, where enthalpy versus temperature we have plotted. In that plot, you can see that enthalpy is going on increasing with respect to temperature. Why is it so? Because Cp always positive. So as dH also will be positive if dt is increasing. dt is positive, means temperature is increasing. And when it cuts the 0 line of the temperature, that we have taken that in 0 line of the enthalpy, here enthalpy is 0, that temperature is 298 Kelvin. This is the standard condition. It is actually general assumption. It's a scaling kind of things. It's the assumptions. It's standard condition assumption. So at 298 Kelvin, H298 equals to 0. Below that, H is negative. Above that, H is positive. Very obvious. Now we can understand from this equation dH equal to TdS. This expression is very important. And then S we can calculate 0 to 2 Cpt dt. If we integrate that, then slowly we can get the entropy value. And this is the third law already we have told. Now check the entropy versus temperature in absolute scale plot. Here the entropy we are talking about is a thermal entropy. We are not talking about configurational entropy. At absolute 0, thermal entropy must be 0, but there would be chance of getting some amount of configurational entropy if some disordered system or disordered phase you are considering. So now we will only focus on thermal entropy. So ds by dt, you can check that Cp by T. So Always we understand that Cp always greater than 0 means it is a positive quantity. So always you will see that ds dt, the slope of this plot, always positive. Always it will be positive. So as temperature is increases, always entropy will increase. So we can say that rate of entropy change will be decrease if temperature increases. Then you have to take Cp is constant. Okay. So if the Cp is constant, if you check that Cp is not going to change with respect to temperature, then only you can check that ds dt is decreasing as temperature is. But this is not possible in realistic manner. Cp also increases as temperature increases. This is a very good hinge of the solution. But we can tell that ds dt always greater than 0 or positive. But that rate, how it will going to vary, that depends upon Cp as well as T. And Cp is a function of temperature, then you cannot say that ds dt is decreasing if temperature is increasing. It's only possible when Cp is constant. That is very rare. Now, gives free energy equals to enthalpy minus Ts. And we know the enthalpy is equal to internal energy plus pressure multiplication by volume, U plus PV minus Ts, absolute temperature multiplied by entropy. Now we can differentiate and get the differential of this expression, that dg equals to du plus p dv, v dp minus tds s dt. Okay, so dg plus, then you can tell that this part is dh and tds also we know that is dh, so that will be cancelled, and then there will be v dp plus minus s dt, and you get that dg equal to v dp minus s dt. So here we understand that there is a differential form of dg, and that is related with that expression with differential of pressure and differential of temperature. Now, if we now want to plot free energy versus absolute temperature, because already we understand the plotting of enthalpy, plotting of entropy. Now we are going to plot the free energy. So free energy, the plot is correct only when entropy is constant with respect to change in temperature, but S increases as temperature increases. So this kind of plot is not correct. If it is only correct when you can tell that the S is constant, means dg by dtp slope at S is constant always, then only you can get the constant or same slope throughout the curve, G versus capital T curve. But in reality, S increases as temperature increases. So the plot is not realistic. So now you can represent free energy G versus absolute temperature in best way. This is the curve where the entropy is changing with the increase in temperature, and that actually changing in the entropy is become higher with respect to when temperature is increasing. That's why you can see that at higher temperature the slope, at this way the temperature is increasing, slope is higher in magnitude, but negative is sign because dg by dt at constant pressure is equal to minus s, and g equal to h at t equal to 0 degree Kelvin. And if you go at 0 degree Kelvin, then what will happen? At 0 degree Kelvin, entropy is 0. Why entropy is 0? Because Cp is 0. And why Cp is 0? Because there is no vibration. So the thermal entropy contribution at absolute 0 is 0. So now absolute 0, if you check what is G? G is directly equal to the enthalpy, G equal to H. And this concept is very important to understand the transformation from one phase to another phase, one state of matter to another state of matter. Later on we will check that. Now, if you see the plot here, we already know that it at 0 degree Kelvin, G equals to H, means free energy, gives free energy is equal to enthalpy at T equal to 0. But as enthalpy will increase as temperature will increase. So if you see that enthalpy increases as temperature increases, that also you know. And also entropy also increases as temperature increases, but Gibbs free energy is decreases as temperature increases. This is the phenomenon. Then you can tell that contribution of entropy towards the Gibbs free energy is more dominating with respect to enthalpy contribution. You can get such kind of notion from here. But our aim here to see the plot, if we take a tangent any point of the plot and when it meet in the absolute zero line of G, that is y-axis, y-axis, that point actually tells that at that particular temperature, at that point, it is the enthalpy contribution. This is the contribution of enthalpy. So in this way, from G versus absolute temperature scale, you can determine the enthalpy. Now, I want to plot both free energy versus temperature as well as enthalpy versus temperature. Now the plot would like that, it will be like that. Here this point is H298, that is equals to 0. So this is 0 line of the enthalpy, and in this y-axis the H and G both are plotted. So at absolute zero temperature, if it is the absolute zero temperature, H and G both are equal. So G equals to H. So that's why this point they are touching to each other. And after the as temperature is rising, what will happen? H is increasing in positive direction and G is decreasing in this way. This is the scenario. And any point, if you want to check the distance between these two curves, that actually represent T into absolute scale T into entropy S, Ts. That is also understood from G equals to H minus Ts expression. So fine, we understood that H is there, you can plot, G also plot in the same picture or same figure, and then you try to correlate between H and G, and that correlation term or the deviation from H and G in between that, we are finding that Ts is important, means entropy. So here all the important parameter, enthalpy, entropy and free energy are present. Now, for understanding in this kind of process, chemical reaction, transformation of metallurgical phase transformation, and all those things, why Gibbs free energy G is at all necessary to understand? Why we need to understand that Gibbs free energy concept? Why? It is what is the reason for that? And in the perspective of the stability or feasibility, what is the reason to understand the Gibbs free energy? If we want to check that, take an example, a pure metal. A pure metal can be present, can present in a form of three different states: solid, liquid, and gas. So there is a chances of transformation from solid to liquid, liquid to gas, or gas to liquid, liquid to solid. So if we check with solid state of that any pure metal and liquid state of any pure metal, then try to understand how, if they are transforming from one state of matter to another state of matter, what is going to happen with respect to these three parameters. First, we'll check with enthalpy. So if enthalpy we are checking, then enthalpy of liquid is greater than enthalpy of solid. It is well known. Why is it so? Because enthalpy of liquid or any enthalpy depends on Cp, and Cp of liquid always greater than Cp of solid. Why is it so? Because more degrees of freedom in the liquid and there is a vibration and all those things are more. So Cp is higher in case of liquid with respect to solid. That's why the enthalpy of a liquid always higher than enthalpy of solid. So if it is there, then it cannot be a criteria of stability. The enthalpy cannot be a criteria of stability, because if you go above melting point, liquid is stable, and if you go lower melting point, less than the melting point or below melting point, then solid state is stable. But if you fix a criteria based on enthalpy, you cannot represent why, what is the reason behind sometimes liquid is stable, sometimes solid is stable. So this is the one important thing. That's why enthalpy cannot be the stability criteria for any kind of transformation or transformation from one state to another state, or any reaction, any transformation. Then okay, fine. Now if you want to check, then next parameter is entropy. We can check with the entropy. It's possible to get certain criteria with respect to entropy for finding the stability of a particular phase or system or state of matter. So if you check entropy, entropy also always it will increase from liquid, from solid to liquid transformation as the temperature is increasing. So how it will represent stability of liquid at higher temperature than melting point and stability of solid lower temperature of melting point. So entropy also cannot represent it's properly comprehensively the stability criteria for the phase transformation. So now we have to come another thing. We have to rely on free energy versus temperature diagram. And here we are going to understand about that how free energy is changing with respect to temperature for liquid and solid. So if you check this, first we can draw G solid. This is a solid. This is a free energy solid curve. Okay, suppose this is the line. Now we got a line of G solid schematically. Now we want to draw the G liquid. So now how to draw that? Now for G liquid, what we already know? We know that for liquid state, enthalpy at even absolute zero is higher than the enthalpy absolute zero of the solid state. So the starting point of the curve for G liquid will be higher than the G solid touched to the 0 degree Kelvin line, the 0 Kelvin line, because at higher that H liquid is much higher at absolute zero with respect to H solid at absolute zero. So that's why starting point of that curve will be there, because at absolute zero, free energy of a state or matter or phase is equal to its enthalpy. So that starting point will be high. Now we fix the point. Now we have to check the slope of that curve. What is the value of the slope? Minus S. And which one has having higher entropy? Obviously liquid will have a higher entropy. So the slope will be much steeper, although that will have a negative magnitude. So the curve will be like that. That's why it will intersect with G solid. So that is the reason, because the slope is much steeper with respect to G solid. The slope of G liquid curve is much steeper with respect to slope of G solid. That's why G liquid and G solid, that two free energy curves are intersecting to each other. Then if we can get the temperature at which temperature that two plot or those two curves are intersecting, then we can determine that the temperature is melting point. Because at that point, both having same free energy, so they can equilibrium state, they can be in equilibrium state, they can coexist. Two phases can be coexist. So they coexist at that point. So melting point. So now if you check that from this plot, if we fix free energy as a criteria of stability, then we can tell that lower free energy will be stable and higher free energy will not be stable with respect to lower free energy state. Now if you check, G solid is less than G liquid for T less than melting point. Here you see the G solid is lower. So that's why less than melting point solid state of a pure metal is stable. If you are going beyond melting point, then you are finding that liquid is stable above Tm as G solid is greater than G liquid, because now the G solid is higher than G liquid if you are going above melting point. So in this way, the Gibbs free energy is representing the stability criteria for this liquid and solid state of a pure metal. The example of what I have taken. Now, there is a important concept. Thermodynamics talks about feasibility and stability. Already we have told, or we have learned it. But seriously, it is not confirming the event will surely occur in reality or not. It is not going to confirm it, because that thing requires the kinetic understanding. If you check with the G curve with respect to certain factor, it can be reaction coordinate or anything, then from A state to B state, if you check, in between there will be a activation energy barrier. One has to cross to reach A state to B state. So that actually very important part. It's related to kinetics. It's not related to thermodynamics, but that also influences certain phenomena in thermodynamic domain. Suppose a liquid transformed to solid state. Then, as per what we understand, that if it will cross the melting point, immediately solid liquid should transform to the solid, and in this way it will happen. But that is the feasibility condition. Thermodynamics can only tell that yes, if you are going below the melting point, then there is a strong chances of formation of solid state, or stable state is solid state, because at below temperature of melting point temperature, solid state is having less Gibbs free energy with respect to liquid state. That's why here you are going to get the as a stable phase solid, but it is not confirming that transformation will surely occur or not in reality, because this plot is requires equilibrium condition. And if you see actual case, if you put any, you are taking any furnace or any crucible, there you put certain liquid metal and try to measure the temperature with the help of thermocouple, and with respect to time, if you check actual temperature, then you will see this kind of practical curve. There you will see certain dip in the temperature, and their transformation is occurring. That is called del T. That is actually undercooling. So in order to get actual in reality the transformation, the degree of undercooling or that undercooling is essential, because the deviation from equilibrium condition is required, because driving force is important. Now you have to understand what is the driving force. If you check previous slide, if you here means temperature is much lesser than the melting point, then this distance from G liquid minus G solid, this difference is actually the driving force. But if you reach in the melting point, then the driving force is zero because G liquid equals to G solid. So G liquid minus this G solid equals to zero. So there is no driving force. So you need certain driving force. Although it is a kinetic domain understanding or concept, but you need certain driving force to occur the transformation. So for that, you need that kind of undercooling concept. You cannot suggest this way a transformation. It is the equilibrium kind of conditions. Here you need certain driving force. If it is a diffusion control, then for diffusion, all those things require certain driving force, what we understood from the last slide plot. So this is the important things. Today, I want to discuss up till that only. Thank you.